Stand together.
Yes.
P7, have you tried question number 1? Or have I explained this?
Oh, explain.
Huh?
Explain.
Explain it. First problem and last problem, right? Okay, explain that.
But no do.
What?
Haven't do.
So let me try this question. Okay, this question, you have to identify the target variable in the target region and pass correct argument in the test point function. Verify the function in the test point function. This exercise is OME, so you don't have to download the API. I'm going to download from my to the drive because I saved it. Last week I showed to you right, so I use this card. Yeah, I think we're going to use this one. Okay, so this program is from last week. Okay, I think I reached this point because I said to you before. So, okay, here we know there's a error 4. Okay, these are private. C, which is a complex number. Here is a constant for epsilon. Is delta. Delta step. This epsilon is delta step. Alright, I will not go through these mathematical things. Just try to solve this according to what the instructions shows to you. Okay. So identify the target variables in the power region. As you can see, actually it's already tells you which one is a problem. Okay. And then pass the correct argument in the test point function. Test point is this function. Right? This function. I think I'm going to remove this out. So that we can see it clearer. And this one I'm not going to call the name. The name is here. This one is called solve algebra. Solve number 4. And you can see here this epsilon is delta small value, so you can see it is very small. You just try to notch it, right? And inside here actually has the code that we have to do the parallel computing, right? And test point is the one that we want to look at. At the moment, it will not run because it has to pass in the specific parameter inside there. Specific parameter there, which is not available here, but we have to pass it, right? As what shown there. Then pass the correct argument in the test point function, and then identify atomic function in the test point function. Because when you pass in the argument, most probably the argument is shared, right? So you want to see which one that is shared, and you will protect it. Okay? And here is the test point where you need to put in here some arguments there. Right? And then you get into here, and of course you have to change this as well. Here what we pass in there. Alright? And here we already identified what is the prime value, which is C and epsilon. And here we already managed to identify that. But you have to pass the correct argument. You have to do this, and then you have to identify the atomic function in the test function, which is shared among the tracks, and it needs to be protected with this top one atomic. Okay? Once you finish that, you should get a value something similar like this output, rather than the output that you see here. This output is wrong. You run the program. It's wrong. It's not this value. The correct answer should be 1.51065. So you have to get that value here. Okay, in order to know whether you succeeded or not, you look at this final value that is supposed to be achieved. Okay. Now remember here you have to go to properties, go to C, language, and then click yes here. If we don't click yes, you're not able to use this API. Sorry. And that one too is used here. Okay, once you pass in the correct value into here, and then you do the atomic protection of certain variable, then you should be able to get the answer. At the moment, you would, if the answer is wrong, is because of this missing part, where you pass in here, accept it here, and then process it. And you can see already here, not outside. It already give you the hint that this is a shared value that you pass in. Okay? Yes, here actually it tells you what it is doing, model. This model will iterate. It will iterate this, doing this computation inside here. And here is more complex because you are dealing with real number and also complex number. Right? So we've got real number here, and then you've got the complex number here. Right? That's why it is a bit more complex. Okay, but actually it is doing what it shows here. So you can iterate through, take this z, which is a complex number, multiply it by z again, okay. And then you plus with c, okay. And then you check this, the magnitude of this z here. Here this magnitude should be greater than 2. If this is greater than 2, then you increase this one by 1, and then you break. Okay, when you break, you get out of this plus 1. Okay, from here you can see already the order parallel for loop, meaning that multiple processes is going to execute this loop. Okay. So all of them are going to execute this. You don't have to worry about the C, you don't have to worry about the epsilon. Here's is the epsilon. It's a symbol of epsilon. Yes, epsilon. Okay, it's actually delta stack, a very small stack. Okay, and then you call this test point, the test it, and you have to pass in some value inside here. I think that value is related to the stack. Yeah, this one. None outside. So this none outside is none outside is global. So that's a none outside. You can see from here. It will add this, right? But that one is shared and it's on outside. That means it's global. Okay? So this one, you know already you have to do atomic. So I already give you two answers here. Okay? So what you need is to pass in the value. Pass in the value here. Pass in the value here. And then it's supposed to receive here. Okay? And it's supposed to compute here. Right? So what do you think that you need to pass in? What do you think that you need to pass in? Okay, you see carefully there. The C is actually global, isn't it? It's global, right? But then if you look at here, we are using private there. You see the code private. Okay, that private actually is not right because you need to get the. You need to get the. We initialize the C. No, we did not initialize the C. So I think it's okay. Yeah, I think it's correct. C is correct. How about epsilon? Yeah, epsilon is not right. C probably is right. Epsilon is not right. Okay, why C is correct? C is private, but we need to initialize it. This C. We need to initialize this C. Kind of weird. How come the C is initialized? Okay, C is not initialized. Yeah, C is not initialized, right? Because if you look at the code inside there, C is actually getting this value, right? So C is a private, but we don't have to initialize. Okay? Now how about epsilon? Do you need to initialize? Okay, it shows that it's private, but do you need to initialize? Do you need to initialize? How do I know that this C you don't have to initialize? The reason is because when you come in, you can see here, it is actually written. It is not used, but it's written. Right? So if you put any initial value, you'll be overwritten. Right? So you do not need to initialize it. So that's how, even though you do not know what this formula is all about, but you can see from there, C is not used, but C is written. So when you come into this statement here, this order statement, C is not initialized. We don't need to initialize. It's a private. We don't need to initialize it. But now the question is, this epsilon here, do we need to initialize it? Do we need to initialize? That means, do we need to initialize? That means get the value from somewhere. Do we need it? If yes, why? Look at the code. Look at the program. Even though you do not know what this code is doing, but roughly you can guess. Okay, I don't explain it because this is very mathematical, and I don't have time to explain it. But you can see from there, even though you don't understand this formula is fine. We know that EPS, it wants it to be private, but do we need to initialize it when we enter? If yes, why? I already told you that C, you don't need to. C is private, but do we need to initialize it? I said no. The reason is because if you look at here, it is not used, but it's written. Right? So if we initialize it, it's pointless as well, right? Because anyhow, when you enter, it gets written. Now the question is the epsilon. Do you need to initialize this?
Yes.
Why?
Need to write
Why?
What's the formula?
Huh? What? Why do you need to initialize it? Just look at the code, you can know already. Why do you need to initialize? You said yes, it's correct, but why? Why?
Need to pass the epsilon, so need the value.
That one later. But from this code first. Why do you need to initialize it when you enter? When you enter into this pragma here. Why do you need to initialize? It's private, we want it to be private. But then do we need to initialize the epsilon EPS? You said yes, I said it's correct, but why? Look at the code, just look at the code only. You don't have to understand the formula.
you should know. I already give you the hint just now. What is the difference between this C and this epsilon in the code there? What's the difference? This one you just need to use logic only. You don't have to understand the code. You just need to use logic only. Very simple. If you don't initialize, if you use it, what is going to happen?
Down.
It's not say error. It's garbage there.
Down.
And can you use it? Definitely you cannot use it. You cannot expect something to be there. If you expect something to be, it will be a random number. And it will never be correct. Right now. Which means this one must come from outside. You can see from outside what is it written there? What is it written?
1.0.
Yes. So if I put private, this will be created as private. That means these two are different, but with the same name. And it will not carry that value, it will carry a random number. Will it be correct? No. So what should you put for EPS? How do we initialize it? Okay, if you don't know, look at the practical 7. Look at practical 7, it has a hint already here. Look up here. Which one, what do we need to do? This one I explained to you last week, right? Yeah? Okay. So what should we do here? What should we do to this EPS? I already helped you this far, you should, come on. What should you do to this EPS? It should be, I told you that it should be initialized to the value outside there. So what should we do to this EPS? Huh? Refer to P7. I already explained to you P7 last week. Okay, this P7. What should you do to this EPS? C is fine. You should put it as private. But what should you do to this EPS?
Is it use a get trade number?
Huh?
Is it use the Prama get trade number?
No.
No.
Look at P7. Yeah. I already explained to you last week. Did I explain to you this? Did I explain to you? I did, right? Because if I don't, I won't be writing this code. And this code actually comes from my Google Drive. My Google Drive has the day there. When I save it into your folder. Okay, this one must be this one comes from Thursday folder. And my code was here. It means that I have already explained to you first private, last private. Is that true? Okay, refer to that first private and last private. Alright, now come back here. What should you do here? Okay, what is first private? What is last private first?
But first is C.
Huh?
C is the first private.
Pardon?
Epsilon is the last private.
No. Answer me first. What is first private? What is last private? What is first private and what is last private? Last week I mentioned to you, right? What is first private? What is the last private? If you don't know, look at the P7. P7 actually explained to you. In fact, you can just read P7. You don't need me to actually tell you. Okay, last week I tell you because I know that you're not going to read. But right now I already explained to you. Right now you have to read. If you forget what I explained, you read. Read P7. So there are two, first private, last private. What is first private, what is last private? If you don't understand that, you're not able to do it. What is first private? does first private do? On. I think you should read this. If you don't read, I don't know how to advise you. Because the text actually tells you very clearly what first private is doing. What does first private do? What does first private do? The text actually tells you very clearly. What does first private do? Can you read it first, please? Because if I explained to you last week and you didn't, perhaps you didn't hear what I said, or you forgot what I said. So now I ask you to read. What does the first private do? In fact, the answer is in there. What does the first private do? Anybody? Yeah? What does first private do? Huh? Yeah? Can you say in full?
That all the variables have initialized with the same value.
You actually go into the second part already, the first part. What you say is correct, but that is the second part, the first part. I want it full. Because you say initialize, your friend will not know what you're talking about.
Each thread will have one instance of variable.
And then? And then?
And then the second part.
Explain in full, good God.
And then the variable initialized with, and all the variables initialized with the same value.
Okay, what he's saying is this. Okay, this is, actually it's written down here very clearly. T is global, right? But you want to create a private one inside here, and this T is actually a private one, different from this. Even though it's the same name, but it's private. Okay? If you put private, you will create it without initializing. But if you put first private, we explain here. The first private is T is private variable. It is different from this, except that it is initialized to the value outside. Right? Okay, so my question right now, come back to the question here. Epsilon, we need to initialize it. So what should we do to this? Should we use private or what? What should we use? What keyword should we use? On.
Last private.
Huh?
Last private.
Last?
Oh, first private. So yeah.
First private. That's all that I want to know. Whether you understand or not. Do you understand right now?
Oh.
The problem is you never read. Actually, it's very simple. Correct or not? It just say very clearly there. First private. Initialize. I already keep telling you, you need to initialize this. And I ask you what you should put here. First private, right? Okay. Come back here. There's a mistake there. You have to fix that. Okay, C is private. You don't need to initialize because C, you are only writing it. Okay, so you don't have to initialize. So leave it there. There, but EPS actually is epsilon. It's a Greek character. We cannot put it inside the private. You have to do it differently. You have to do it this way. Okay, that's the first thing that you need to fix. Okay, fix that. Okay, once you fix that, you have to pass in something here. What do you need to pass in? Okay, let's have a look at Do you need to pass in? Okay, you look at this code here. Okay. What do you need to pass in? The test point is, it tells you this. You need to multiply Z by Z, and then you plus C. Okay? So the question now is, where do you get the C from? Where do you get it from? Okay, what are you testing first? You look at this code here. What are you testing? What are you going to test? If you look at this code here, and then you look at this code, what are you testing? What are you testing? Okay, before we go into that, maybe here is a bit confusing. You see there's a C, there's a Z. Right? There's a C, there's a Z there. And you see there's one equation, say C, Z equal to C. Right? Alright? And after that you multiply, you look at the equation, and that equation is really this one. You multiply. Right? This one is a bit more confusing. But you can see that it right into the Z, right? Okay. So why not? My first question: why not we don't use the Z? We just use C here. Would that be correct? Because Z equals to C, isn't it? Can I eliminate this Z here? I just replace all this with C. Can or cannot? That's my first question first. Why? Why cannot? Yeah, it's true, it cannot, but why? Two dimension. No, actually Z and C, both of them are complex number. You have imaginary and a real number, alright? But I don't want to get into that. Just look at the logic here. Just look at the logic. Alright? So Z will take the value of C. Right? Both of them are complex number. I just copy over the value, right? But my question here is, why do they do it like this? Why not just, because Z is equal to C, why not just replace all this with C? Okay, why I ask you this question? Because first thing is because you do not know Mandelbrot, right? But I have to explain Mandelbrot. Actually, it's quite lengthy. I don't want to go through that. Okay, in order to able to program this, you don't have to understand Mandelbrot because the code is already written. You just need to use your logic thinking, look at your code, and then figure out what is supposed to do there. All right. Now I'm guiding you. Okay, Z equals to C. Okay, and why do we need to do that? My question is, can we remove this and we put C, all the Z we replace with C? And he said cannot. And I said correct, yes, we cannot do that. Otherwise the answer will be wrong. Why?
Is it because got the CL and CI already? If we replace the Z with C, it will like the crash because maybe override the
Override. How does it override?
Because the CI and CL we need to pass the value. I think it's get from the soft Mandelbrot part. And the ZI, if we replace with CI also, maybe the value got no correct.
I think you're actually gone too far. Okay. What he's saying is the other part. I haven't reached that part yet. Actually, you're right. Okay. But my question is not that part yet. I'm just asking this simple question. Can we replace this Z with the C? I will explain to you. You're right on that. But I haven't gone to that part yet. My question here is this. Can we replace Z with C immediately? Just looking at this code only. Can or cannot? You say can, why? You say cannot. Huh? Yeah, Z equal to C. The first line is Z equal to C, isn't it? Yeah, 6 is fixed. But then you replace Z with C, isn't it? No, actually, yeah, correct, you're right. What this code is test point is trying to do is this. We want to test whether this point will lead us to that condition. The magnitude of the Z must be greater than 2. Yeah? So the magnitude of this Z here is greater than 2. Actually, that test is this test here. Yeah? So the magnitude, how do you find the magnitude? This is how you do it. Okay, you take the complex number, you multiply them, and then you square the imaginary and the real, and then you add. Okay? Basically, the magnitude here, let's say is C, right? This is a complex number. Let's say C is equals to, I just give you an example, 4i. Okay, this I is a complex number, complex part. Okay? If I want the magnitude of this C is actually 3 squared plus 4 squared I squared. Okay? And this I squared is actually minus value. That's why we want 3 squared minus 4 squared. Okay? Here actually not quite right. Magnitude of 2. Okay, I'm not sure why the formula is different here. But right, it should be something like this because I squared is actually complex number. When you square the complex number, it's actually minus 1. That's why there's a minus. Okay, just assume that this one is correct. Maybe above here they do something that change the formula slightly. But right, it should be something like this. Okay? Now, suppose that this is correct. Okay? Suppose this is correct. So what we are trying to find is the magnitude of this Z must be greater than 2. I think they must have done something different here. That's why this value is 4 rather than 2. Okay, but assume that this is correct. Why this Z here we cannot replace with C directly? You have the answer? No answer. Okay, the reason is this. If you look at the formula, okay, actually I can use it, but let's look at the top there. Z equal to Z squared plus C, right? Yeah? And this C actually comes from somewhere, right? And then if you go into the for loop, and you keep on completing this again and again, will that Z change? But C shouldn't change, right? You don't want this C to change, but you want this Z to change. That's why you need to have Z. You cannot replace like this. You cannot do like this. Because this is not the same as this if it is in a column. Okay, that's why we have to create another variable here. Initially, it will be the same, but after the for loop iteration, the value will change. But we don't want that C to change because we want the actual real number of C, actual imaginary of C. You understand? Okay? Okay, so right now, we know that this Z must be a separate one. right? And we know that this is also a private value. Now that C is not inside here, it must be from outside, correct? Is it correct? It must be from global. And why can it reach here is because it's global value here. Is it correct? Okay. Now, this one is not initialized. Is it correct? And we use it here. Doesn't seem right, right? So where should this C come from? Look at the code here. Where should that C come from? Come from? Yeah, and this C is? The variable C is?
Test point.
Is it the same as the global C just now?
No.
It is? Yeah, it's not the same. What is this C?
The answer of the formula.
The C is private C.
Oh.
It's a separate C. It's not that C. Alright? So we know that that test point actually grabbed the wrong C. It grabbed the global C. By right, it should grab from which one?
The private.
Yeah, it should grab from here because it computed here. See now? So it means that this one needs to get into the test point. How do we make it enter into the test point? How do you do it? Yes, you have to pass, and then what should we put here? What should we put here?
C.
Yes. Okay? We have to pass the C in. You cannot allow this test point to use this C here, because if you don't pass it, you will use this C, which is wrong. Right? Cannot? Because the Mandelbrot actually compute inside the soft Mandelbrot actually compute the C. And we have to pass this private C, not the global C. You cannot use the global C. Guess where we have to pass this? Okay, since we pass it in, what should we change here? What should we change there?
Last private C.
Huh?
Private C.
There's no private here because you're talking about C language right now. Yeah, private C is true. But what should we put there? We should replace the white with? Huh? Yes. D complex. D complex. And C. Okay. Right. Okay, you can use a different name. Let's say you can use D, and then you have to change this D as well. Okay? Okay, so right now we know, now it looks more correct. Right? Okay, so, okay, next. Next is, what is the variable inside here which is global? Is Z global? Is that global here? Huh?
Yes.
How can it be global? Look carefully. Is that global? Is that global? No, why? Okay, what I'm teaching here is this. Even though you do not know, actually you can answer this question. Okay, you just need to use your logic on it. Right? So my question here is Z global? No, why? Yeah, it's defined there, right? It's defined there. It cannot be global. Okay, next. How about ITER? ITER. Private as well because it's there. 10? Private. Okay. How about C?
Global.
It comes from outside, right? Potentially there will be race condition. Is it correct? But when it comes from outside, if you look at the outside here, this C here is, we pass it in, right? But that C is it private or global?
Private.
Private. So meaning that inside there should be also private. Alright. Because when you pass it in C, who is going to pass in is that process. That process is owning this seed. It's not shared even though it passes in. So this actually is private as well, although it comes from outside. Okay? So this is also private. So we don't have to worry. If somebody write into it, fine, because there will be no race condition. Right? Because it's private. Okay? So we know all this private. How about Z? Z is private. M is what? Some more? None outside. Okay. Is this none outside? Global or private? Global or private?
Global.
Global. It comes from here. Okay. So here actually will give you the hint. It tells you that you have to protect it. Identify the atomic function to be placed inside the test point. No other variable needs to be protected except for which one? You don't need for the C, you don't need for the Z, you don't need for ether, you don't need for the temp. It should be for?
Now outside.
Yes, it should be here. So the front one should be here. Yeah? Front one atomic here. Front one 20 atomic. Okay, you write it down there. Okay, once you're done that, you try to run the program again and see if it works. Okay, I did not put it full, I think I already identified all the parts already, and then you run the program and let me know if you get the answer. If not, okay, come back to see what else that we miss. I don't think we miss anything else. I think that's all. Okay, because the formula is actually given, I assume that the formula is correct because I haven't gone into it yet. But the formula doesn't appear to be what it says here, but I assume that is correct because maybe the computation before it comes to here, it has already done something to it, so the formula here will change, right? Because if you want to find the magnitude of the Z of a complex number, this is what you do. You square this real number, you square this imaginary as well. But when you square this imaginary, this will turn into -1. So there's a minus, but I don't see minus there. I think something has been changed up here, which is different from that formula. Okay, and I also see this value is 4 rather than 2. Okay, I assume that is correct, right? Because I'm not going to go and decode it and figure that out. Okay, try that and let me know if it works. Huh? What answer you got? 1.514181. Yeah, and then it is the same as what it says down there, right?
Yes, but from the very beginning, because you're not changing it still gives me the same thing. So
No. It will not give you the same answer. It will not give you the same answer. You try without. See? If you try without, you should get this answer. You get something different. Yeah, you can see from mine. It's 5.625. Yeah, after you change, you should get close to that number. It should be around 1.51. Not exactly, but around there. Because there's a plus minus there. Okay, if you get it, that means it's more or less, I mean, it should be correct. Do you get it? Get it? Huh? No, go and find out what else that you miss. If you run the second time, do you get the same answer? You run the second time? Before you change? Also this value. What is it? No, before you change, you make the change, it should give you a different number. because it shouldn't be grab, because what you use is a random complex number, because the global actually it's not initialized, it did not pass in the completed value. It can be any value, right?
Well, I don't get the wrong answer, but it seems like it's a deadlock.
Deadlock.
Question.
Original one, deadlock.
I just removed the graph for C.
Right. Oh no. No, you try the original one. If this code actually is the original one, you should get something like this. The original code should get like this. It shouldn't go into deadlock also.
The original one still gives me a high answer.
How about the rest? Because I don't get the answer. And you shouldn't get it can be the correct answer also, because you see here,
I don't know.
because this C is not initialized, right? So it can be any value here. So in your case, maybe that value is very close to 1.5 in your case. Okay? In my case, my value is random number, and it doesn't appear to be 1.5 something. It was 5 or something. Okay, how about the rest? Original file, if you run, you should get something like this. This number is actually a random number also. Okay, it can be 1 point something, but I believe it will be different from 1.5. Anybody else? Do you get a different one? Original value. That time you get the answer already. After you want about 1.5 something like that. Okay, it should be around that. This part here, actually, the C does not need to be first private. The C just needs to be private. Yes, C just needs to be private. But epsilon needs to be first private. The epsilon needs to be first private. C is private, but this epsilon is first private. Put it outside. Put it outside. Actually, it should be the same answer. Because this C here will actually you can put first private, but it's pointless. Because you don't initialize it. It's pointless to initialize the value.
Okay.
This one is first private.
Okay.
Yeah, the value will change, but the value will be around because there's a plus minus. Right? Okay, it doesn't need to be 1.5, but it's close to that value. Okay? Yeah. Okay, it's very close. Did you run before and after? I suggest that you do that. Because you have to do the comparison, before and after. I suggest that you do before and after. Okay? Before and after, how do we do it? Okay, before and after, right? Now I already changed this. So, I copy this and then revert to the previous value. So I'm going to put this like this. The original one was private, yeah. And then what else? There's nothing there. Okay, let's
let's call this O copy. Okay? And this one is O. The O1 is wrong. Okay, and it doesn't have prop mark. Okay, this is an O value. Test point O. So it's solve O memory block. Okay, I'm going to call that. So I got two there. This one with the solution, this one without changing anything. Okay, so the O1 is this. Okay, if you run, you get something like this. Okay. If you fix it, then you can run this together. Okay, if you fix it. But in my case, I did not fix it. Okay, I get this value because I didn't fix it. I only pass this, which is correct. Yeah, and then I did not fix inside there, so it's still wrong. Here, so I did not fix it. So wrong. Okay, so the O1 is exactly like O1, and I call it test point O. The test point O. I copy another copy of it, and I revert it to board. Okay. The new one is this one with the D complex. D complex C. Okay. And then the new one should pass this way. Okay, you have to change this as well. Change this. And then that pragma OMP atomic. Okay? If you do that, then your answer here, this answer will be 1.5 something, very close to this number. Okay, there's some error there, plus minus. Okay, leave this one as private. This one is the first private. Did you do that?
Which one private? Which one first private? No, you have to change it. You did not change it. This one is wrong.
Oh,
Is it the new one or old one?
O1.
Old one. Okay, the new one you have to change. Right. Here's the new.
New one. Is it right like this?
Yeah. Oh yeah, correct. Oh yeah, another part that you need to do. I forgot to mention it here.
Okay. If we look at here, I, J, forgot this one, I and J. That IJ is from outside there, okay? And all this needs to be executed in parallel. Is it correct? It needs to be executed in parallel. So this I and J, is it shared or not shared? If you leave it like this, is it shared or not shared? Huh?
No, sir.
Not shared, why? Why is it not shared? Where did this I and J come from? Outside there, right? How many copy? How many copy? One copy only. But this is OMP parallel. That means multiple thread is going to use this I and J. Now they are sharing the I and J, right? Is it correct? So is this I and J needs to be made private as well? Do we need to make it private? If you don't make it private, they are shared and they are writing into it. What is going to happen? Raise foundation. So, and in fact, you shouldn't share. Actually, it's nothing to do. Yeah, it's raise foundation is wrong. But here, they shouldn't share. Right? The I and J, it should be a separate I and J. So it should be private, and it should be inside here. Okay? Move the EPS out because that is first private, but IJ
Now, ij should be private or first private?
I private.
Yeah, private, because you don't need to initialize. Outside there is not initialized, right? And here actually it's initialized, 0, 0. Okay? So you don't have to do first private, because you can do first private, but it's pointless. Right? Because you actually initialize it, but later on you're going to override it. It's pointless, right?
Mm-hmm.
So it should be private. So you're right. So private is IJC. What else? No. IJC. First private should be epsilon EPS. Okay? Okay, if you do that, then you should get the answer. Did you get the answer? Is it close to 1.5? Yeah, you should get 1.5. Once you make that change, I think you missed that just now. I forgot to look at this I and J just now. Do you get it?
Yes, I can skip a long answer from the author already.
Okay. I, J. Just forward. Okay, you should get something like this. Okay, the first one is wrong. The first one is original program. And this is the one that I modified. You can see the value actually is very close. Okay? Of course, I understand Mandelbrot, but you don't understand, but it's fine. As I told you before, you just look at the code, you just think logically. Okay? The one that I guided you is what you should do. If let's say you don't understand this formula, it's fine. Okay, you just need to know what is shared, what is not shared, and look at how it is used, and then you know whether it should be private or first private. Okay, and also there's certain part I and J just now we missed. We know that it's used and it shouldn't be shared, so it should be private. I and J. Okay, so those are the things that you need to understand in order to do this part. Yeah, I know that is kind of complicated because I don't have time to explain this number problem.
或者
Look
搞
at the
就是
equation
你要
is
看
very,
有
very
的
very
东西是这样。
Okay, actually it's fractal. Fractal means if you graphically if you zoom in,
我婆婆她就是
okay,
就是
you see the formula recurring.
这整个
Okay,
是
the image will recur.
跟着老
That
师
means the
改。
image will repeat. So that means you can zoom in indefinitely without hitting any bottom image, I mean fundamental image, because it will keep on repeating. Yeah. Alright, let's move on to the next one. Consider simple list traversal like this. Given that we have covered about 1 day, how would we process this group requirement? Can we process this group requirement? Okay, we are looking at, I think this is another question. I'm not sure why it is placed in here. But this is a separate question already, because it has nothing to do with the previous one. Previous one, we don't have this list traversal. Okay, what is it called list traversal? Let's look at this one. I can explain because it's simple. Suppose you have a linked list. I think all of you have learned linked list before, right? So linked list, you have some data here, and then you have a pointer pointing to the next element. You got another data here, and then you got another pointer pointing to the next data, perhaps. And then if this is the last one, you will be pointing to now. Now that is 0. Okay, that's the indicator, that's the end. Okay, so you must have some pointer that is pointing here, Okay, maybe this one is called head. So the head is pointing to the first one, and you can see this is a linked list. Right? It's a list of items. So this item contains the data, it can be any data, right? Integer, float, or whatever. And it has a pointer, which point to the next one. Okay, so you start from the head, so you assign P to head. So P equals to head. Okay, so P right now is pointing here. The same as the head, right? Now, inside here, you see the while loop. Okay, this while loop will traverse. Traverse that means travel. Okay, you travel from the head, move to the next one. Move to the next one. Okay, this pointer here is called next. It has a name, it's called next. It's next. Right? Next. Next. Okay? So if you see carefully the code inside the while loop, we process the P because P contains the data, right? So we process it. Right? And then you move on to the next one. So P is a pointer, so you have to use that pointer to access this next. Okay? P next. And then you assign back to P. P next. Okay, so currently your P is pointing here, right? So P next is this value. Now this value is assigned to this P. So right now this P is not going to point to there anymore. Your new P is pointing to here right now, after you execute this. Okay? And then it will process the P again. It needs to process this data. Right? And then the same thing, when you hit this, P next, get this address is pointing there, and then put it back to P. So right now your P is not pointing there anymore. Your P is pointing there. And then you process again. Okay, when you perform the last P next, the P next is now. So you assign now to P. So P right now is pointing to here. And then when you reach this while loop, the next iteration, you find out it is now. So it will break from the loop. You get out from this loop. Because P0 means false, right? So you get out from it. So basically, you travel from the head until the end and then stop. Okay, you understand this code here? Okay, the question here is, how do you process this loop in parallel? How do you process this loop in a parallel? Can you process this loop in parallel? Okay, can you process this loop in parallel? Okay, assuming, what is assuming here is this. Most probably traversing this you cannot do in parallel. So you need only one process to go through this. But that one process that is going through this is going to pass to the other process to process. Because this process will assume that it's going to be a very lengthy process. It's going to be very hard work here. Okay? Traversing this linked list is not so hard, alright? Because you can go from one to the next very quickly. But if you want to process this data can be very complex and it takes a very long time, right? So most probably our parallel computing should be in the process rather than in this linked list. Okay? So how do we fix this? Okay, my idea is this. You take one thread to do this. Once you get this, and then you pass to the process. Okay, you process P0, you do this. And then when I reach here, I can go very quickly, right? Before this guy finish this, because it's a very lengthy process, I can grab this one, give to P2. Oh, sorry, this P0, P1, P2. Alright. So right now they all will run in parallel, almost in parallel. You understand what I mean? Okay, so how do we solve this? They use work sharing construct. Okay, this probably is similar like what I mentioned to you, where you read from the hard disk. So for example, you have a picture, right? You have a picture and then you read it. Let's say you want to compress this image. So what you do is you maybe split them into like this. Okay. So who is going to read this is one process. It's the same as the process that is going to go through this list one by one. Okay, when it has this data, it passes the process, the other process to do. When you reach here, it passes to the next process. Reach here, it passes to the next. It's the same thing here. When you read the file, maybe this is the image. Okay, so one process is going to read this image, or one thread is going to read this image. After that, you're going to pass this to thread number 0, thread number 1, thread number 2, thread number 3, thread number 4, thread number 5, and so on and so forth. Okay? So reading might be kind of slow, but processing this is even slower, right? So the concept is the same. Okay, what you apply here also applies it. That means you use one thread to traverse this. Once you get the data, you pass to the other thread to do the job. Okay? So what kind of concept do you use here in order to get that? What kind of parallel computing construct do you use? Okay, there are many ways to solve this, but you can use it anyway. One suggestion, but of course this is not the best solution, is to, if let's say you're doing MPI, right? MPI you can use scatter gather. Right? Because you have one process to read this key and then disseminate this information to the rest. Okay? Here you also can do the same. Okay? First you get the ID of the process, and you, let's say ID 0. ID 0 is going to read this one by one and put it into array. Put this address into array. Okay? Alright? And then you have a barrier. Everybody will stop there until this thread 0 has done this. Okay? When the thread 0 has done, it will come out and you reach the barrier. So right now the rest of the thread knows that all the data is inside the array already. And then each one of them will grab from the array and then process it. Okay? So that is one way to solve it. Of course, this is not the best solution, but it's one way to do it. Right? Unfortunately, we cannot do any exercise for this because this exercise here is requiring you to have a process, and also, yeah, I think that's all that we need. Okay, process, and then you need to construct. You need this data structure. And also you need to put the data inside, it's not there. Okay, but it has some relation to what we're going to do next, which is this question. Then consider the program P7Q2, let's get that. Okay, copy this, and then put it into your code, and then your project. I see there's a, oh yeah, I think here we'll do this as well, right? You can see the structure almost the same down here. Okay, so let's put it here. Yeah, and then bring this up. So all this up. Yeah. And this one I already have, this one I already have, this one I already have, so delete this. Here this one is to define that.
this is kind of lengthy. I'm going to change this. Constant integer n equals to 5. Much easier. Equals to this. Try to eliminate old style of programming. Here, new style of programming, they use a constant integer. Down here, and this code here is I can see that. To the next step. This next is actually the next that I was talking about, and the data is this. This two is data. Here, one, but it can be many different data. Okay, and this is Fibonacci. Fibonacci number. I think you have tried this before in the other subject, right? Fibonacci. You heard of Fibonacci before, right? Actually, Fibonacci is very simple, but let's modify this code first. Okay, this one is Fibonacci. It's called Fibonacci. Right? Okay, let's study this program. Actually, this has something to do with the release that I was talking about here. Here has the data structure. So the data here got two data. One is data, one is Fibonacci data. There's two there. Okay, and then you see there's a next there. Struct node next, again, point to its own type. Okay, not point to itself, but point to its own type. Struct node, you can see struct node at the top there. It's the same name, right? Okay, and then this is the Fibonacci. This is the core of the program. And Fibonacci is very simple. Actually, it's this number that you see here. Let's get back to this code. Or maybe you don't have to look at the code, look at this Fibonacci. Fibonacci sequence. Okay, so Fibonacci sequence, only the first two is defined, F0 and F1. Okay, these two is defined. The rest of the number is not defined, that means it's defined through the formula. Only the first number is constant, I should say that, right? So Fibonacci 0, F0 is 0, Fibonacci 1 is 1. Now the Fibonacci for other number is actually taking the previous two. Okay, that means take x minus 2 plus x minus 1. Okay, that means you take this one, add with this one, you get that number. Okay, so let's see how it will evolve to do that. So initially it was 0, 1, right? And this one says, take this number, because this is 2, isn't it? 2 minus 2 is 0, so it's 0. Okay? And that's 0, and this one, 2 minus 1 is 1, right? So F1 is 1. So 0 plus 1 is also 1. Okay? Now, if this is 3, 3 minus 2 is 1, which is 1. 3 minus 1 is 2. Okay, this is 2, isn't it? So 1 plus 1 is 2. Alright? So if this is 4, 4 minus 2 is 2, which is 0, 1, 0, 1, 2. So it's this one. Okay? 4 minus 1 is 3.
is this one. So you take these two, add it, and you get 3. So basically, you know already from that, it's actually taking these two numbers to find out what is the next number. 2 plus 3 is 5. 3 plus 5 is 8. Okay, 5 plus 8 is 13. Is it correct? Only these two numbers is constant. The rest of this number is found through this formula. Okay, and if you look at the back piece here, in order to compute this 13, you have to compute 8. Because otherwise you will not know what will be the next number, right? Okay, that means you need to know what is 5 and 8, the value before. In order to get 5 and 8, you need to compute 3 and 5. In order to compute 5, you need 2 and 3. So actually they are dependent on one another. And this one is very hard to actually make it into parallel computing. Okay, this kind of problem especially cannot be solved using parallel computing. Alright? But then this exercise here actually is not about solving this efficiently. It's trying to solve it in kind of a very fun way. Solve it in like this. Alright? Okay, so if you look carefully here, you can do something like this. If I want to find this, I start from these two and I compute until I reach these two, then I can find 13. Right? Now if I want to find 5, then I compute from the beginning. I also can find this 5 because after that I can compute this 2 and 3 starting from the beginning, right? So basically, we can do something like this. We can assign each process or each thread to compute all this. Okay, let's say I got 1,000 threads. I pass this job to 1,000 threads. Each thread will compute starting from this 0 and 1. Now they can run in parallel. But of course, it's not efficient, right? Why? Because they're going to repeat the computation again and again, which is the same. Is it correct? But this program is dummy program. You just use it just as an exercise. Actually, it's not a good idea. As you can see from here. You can see if I want to find the 5, okay, I need to get from the 4, right? Yeah, I need to get from the these 2. And then for this, I need to get from these 2. But if you see here, isn't that this one is the same as this? Right? So it means that I'm going to assign 2 processes here, and they are going to compute again and again this value. Actually, it's not a good idea, but it's just for an exercise. Just assume that this is the way to solve it. Okay? And if this is the way to solve it now, of course, there's a way to actually do parallel computing. Why? Because process, let's say thread 0 do this, thread 1 do this. Right. Okay? Then they can actually run at the same time and then get the answer, so that they can pass this answer to 5, and 5 can compute the value. Okay? Yeah, right? Okay, so let's have a look at the code. Consider this program travels a linked list computation of a sequence of operation number at this node. Parallelize this program using construct discussed so far. You may evaluate the performance using different scheduling algorithm. There are many other scheduling algorithms here. Okay, try that. I should put this further away from this, so that we know that this one is the second part. Okay, use this code here, and then try to figure out how we're going to run that in parallel. Now, to compute the Fibonacci is this. Okay, this one is the Fibonacci. And then the process work here is this one. Okay, process the work. So let's see how it works. So initially we initialize this. Okay, initialize the list is done here. Okay, how many that we create is dependent on this 10. And this 10 come from the top here. 5, we only create 5, not so many, only 5. Actually, it's exactly the same as this, only 5 up to this point. Okay? Okay, FS38. So we have some number that we initialize inside the data structure, is FF, this one, this data. Okay? The first is 0, right? The first one is 0, see here? Okay? And then you create a new one. So initially you create the first one, which is the head. You create the first one. And when you enter into the for loop, of course, the head actually data is 0. Sorry, Fibonacci data is 0. The data is FS, which is 38. It's fixed for all, 38. Okay? And then when you enter into this this for loop, you will create another one. So you create this one, the next one. Yeah, and then you let the head next point to the 10. Okay? Head next point to the 10. That means right now this is actually pointing to here. Okay? So actually link together. Okay? And then P is equal to 10. That means initially your P is pointing to here, right now your P is pointing here. Right? And then this new data, you put Fs plus I plus 1. Okay, so basically, Fs is 38 plus I is 0 plus 1. So it's 39. Okay? So this one contain data equals to 38. Fibonacci data is 0. Okay? This one is 39. Fibonacci num data is, I don't know what data is this, 0 plus 1. Okay? 0 plus 1. So 0 plus 1 is 1. Okay? And then you repeat. Okay, you repeat again and again. Okay, you repeat. So right now, you're here, and then you create a new one. Okay, here you create a new one. Okay, and then you allow this P next point to the new data. Okay, so right now this one is linked to this one is linked to the new one. Okay, and then next, P equals 10, basically P right now move to here. Okay? So right now P is pointing to this new one. Okay, this one is connected to here and this one is connected to the new one. Okay, and then the data is 38 plus 1 plus 1. So 38 plus 1 plus 1 is 40. Okay, so Fibonacci data is 1 plus 1 is 2. Okay, and you repeat this. Okay, you repeat it. So this will be the linked list. Okay. Alright, and eventually the last one is going to be pointing to now. So you're going to have the last one. The last one is going to be when n equals to 5. When n equals to 5, because n is 5, right? Then you stop. So that last one, this last one, the next is actually going to point to now. Okay? So it's going to link inside that for loop, and eventually the last one is going to be 1. You understand? Okay? And then you return the head, return this one, the beginning. Okay? You return to who? You return to this collar. So this collar is going to hold the head, so it passes to this to the data structure. So the data structure inside this Fibonacci function is going to point to it. Okay, so that init list perform that. Is that clear? Clear? Okay, next. Now we start the timer and we start the processing. Okay, while p not equal to 0, and then we travels there. So initially p is pointing to the head, right? And then it goes to the next. When it go to the next, it process the work. Okay, right now we have the process work right there. Process the work here. Okay, the process work is going to do that. It's going to take the data, p data, which is this one, and this one, and then it will pass to this this function. This is Fibonacci function, and then it's going to compute that Fibonacci number. Okay. All right. So that data is the first one is going to be 38, and it passes into 38. So 38 will go into here. And 38 is going to use this formula to find the value. 38 is quite big. So it's going to take a while when it computes. Right? 38 means 1, 2, 3, 4, 5, until 38. Right? So you have to do all that. So when it does all that, it will return the value. Okay? Finally, it will return the value. Okay? That value will be placed inside there. So that will be the Fibonacci of 38. Okay? Fibonacci. Okay, it's going to be placed inside it. Right? So data is going to be this number, Fibonacci. So this is data. So basically it means this is P data. Okay, and we find the Fibonacci of this data and we put it into Fibonacci. So this code here actually performs this. Is that clear? Alright, so that is processor, and it's going to be quite time consuming because this number here is quite big. Okay? Right? So each of the process is going to do this. One process is going to do that, the other process is going to do this, so there are 5 altogether. Okay? So we're going to assign this to each thread. So one thread is going to deal with one of this data. Yeah? And eventually when it is done, we're going to use aggregate time. Start time is here, end time is there. Alright? And then finally we print out the value. Okay, we can double check whether it's correct or not. We print out the data, and then we print out the Fibonacci number of that number. Okay? And then we move on to the next one. That means we do the same. Find this, find what has been completed, and then find this, we find what is completed, and so on and so forth. So when we finish here, when it's the last one, okay, when it's the last, you get out and then you free the P. Oh yeah. As you travel, okay, you will free. And the last one is free here. Okay, the last one is free there. Okay? And then you print out the time that is taken. So basically you have all the numbers. So we know that here must be the place where your error computing should be happening. Okay? As you can see, the one we get time and all that. Understand? Okay, so we're going to use schedule because I see here it does not mention about schedule, but here it mentioned about the schedule, right? Scheduling type. So go to scheduling type, you see this. So I think this is the answer already. The answer is inside here. Okay, you have to use this scheduling, different type of scheduling, for scheduling. And this for scheduling is going to allow the processing that I mentioned to you. Okay? The first one is going to pass to process 0, process 1, process 2, here is, they call it track 0, track 1, track 2, track 3, until the end. Okay, and then when it is done, everybody will wait here. Sorry, will finish. Okay, everybody will finish, and when you wait for everybody to finish, and then you will continue on. Okay, and then inside here, only the master track is going to do this. He's going to print it out and finally print out the time. Okay, is that good? Right. So we're going to use scheduling. The scheduling is available here. Okay, how many scheduling do we have? We got a different type of scheduling, right? The default one. And you have a static, dynamic, guided, auto, runtime. Okay? So the static is like this. When you do it, you get that. Okay? And if you have, if you want to specify the number of threads, you can specify it. Okay? So this is static. Oh, sorry. 4 here is indicating how many there. Let's say you got 4 threads running. Okay, and then it is scheduled in this way. Right. If you put 8, there's an 8 here, and it is scheduled in this way. Okay. Okay, dynamic. Is dynamically assigned. So if you run, actually this is just graphical view of how actually it is executed. So it looks kind of random here, right? When executed. Right. So you can also specify the number 4, but it is actually quite dynamic. You can see it's quite dynamic. But 4, 4, 4. Okay. This is also quite dynamic, but 8, 8, 8. Okay, guided actually is similar to dynamic. It divides into iteration to chunks. Okay, so just now when I say this number here, actually this number is the chunk size. Okay. Okay, so the guided one will be something like this. Okay, as you can see, the size actually reduced. The size reduced. Of course, it's still dynamic. Okay, auto delegate the jobs to this scheduler. You don't really care, and the compiler will decide for you. Okay, so the compiler will automatically do it for you. Okay, you can try any one of them and see the result. Okay. Okay, the scheduling actually is used for the for loop. So the MP parallel for, you can see there's a for there. And then you can specify what kind of scheduling that you use. Okay, so schedule, whether it's auto, static, dynamic, guided. Okay, and then what is the chunk size that you want to use? Right? If you don't specify, the default chunk size is whatever default value the OMP use. In this case here, I'm not sure it is 3. Here is 16, I believe. 16. Okay. By default 16. If you want different size, you specify the chunk size. Okay, yeah, put 4 and you put 8 there. Right?
Okay, and how is it executed? We execute in iteration. So the first one will iterate like this. Okay, and the second iteration you see here is empty. And then this is actually done by the same threads. So just now I was executing this, now we execute this. Okay, so you will do in. It's just like if we look at the static, it looks like everybody process at the same time, but some will be fast, some will be slow, but they will wait for one another. So before it gets to the second iteration, you wait for all to finish first before you execute it. So that is what we see from this diagram. Okay, I will put it as 4. The chunk size is 4, so 4 and then 4. Okay. And here there's another 4 because it's got 16 altogether, right? So it will break into 4 chunks. Okay, so this 1 chunk, 2 chunks, 3 chunks, 4 chunks, right? So the first 4 is going to execute the first chunk. It's 4, 4, 4, 4. Okay, and then the second 4. So this thread and this thread is 2 different threads. I mean 2 different groups. So the first group, second group, third group, fourth group. Okay. So this T0, T1, T2, T3, T4, T5, T6, T7, T8, T9, T10, T11, until 16. Okay? On the second iteration, you can see that this one, T0 is going to execute this, T1 is going to execute this, T2 is going to execute that, T3, the same thing here. This one is T4, T4 is going to do this, T5 is going to do that. But then within this chunk, they will wait for one another, right? This one will wait for one another, but this will not wait for one another. It can go at its own speed. Okay, but within the group itself will wait for one another. Right? So that is static. Maybe we try with the static first. Okay, and then we use the proper chunk size. So what is the proper chunk size here? Okay, so we know that you're going to use schedule, OMP4 schedule, and we have to determine the chunk size, and what we're going to do is something like what I mentioned to you just now. So this is going to be done by one thread, this is another thread, and this one is another thread, and that is another thread. Okay? So each one of them will be scheduled to do its own task. Once all of them finish, you get down to here, and then the master thread is going to stop the timer. Not stop, sorry, not stop the timer. Get the end time, and then print out the result, and then print out the time. Is that clear? Clear? Don't have enough time. First. Chai Yun, Xu Zixing, Xia Zingyi, Jin Jiaman, Yang Wei Song, Zheng Dashini, Wu Wei Li, Jackson Chai, Jackson up there, Gao Yongjin, Li Shenhai, Liu Weizhen, Hu, Lin Jiayi, Lin Weihan, Junho. Okay. Shun, okay. Han Yu Moon, Son Yutta, Tan Chong Han, Tan Shenji, Tan Xiuyan, Tan Wen Yao, Wong Xin Yi, here. Yi Zhangzhe. Okay, here you need to use a shadowing. Basically, it's just this. You have to use this YP power 4, right? And then after that, the shadowing. Whether it's static, auto, guided, or dynamic. And then the chunk size, you decide the chunk size that you need to use. Now you have to use this because otherwise you will not assign appropriately to the process to perform the task. Okay? For example, that's given here. Okay, you can see here. Brahma YP4 and then shadow. Here you use static and then chunk size is 4. Okay. So just that we refer to this when you do this question. We show to you the static, show you the dynamic, size dynamic, and then it shows to you guided. Okay, auto, and you run all of them. Yeah, you can see that. Right? Okay, put your front arm here. Front arm YP4, only the first part, and then you put the rest in. Okay? So the next one is going to be parallel. Okay? So basically it's just this. See that the comma YP parallel, sorry, comma YP4, and then how you schedule it. I think maybe do like what it does here, like that. You split them into two. So every parallel. Right, and you can also specify what is private, what is shared, how many tracks. How many tracks here? What variable is shared? What variable is private? Maybe first variable, last variable, here. Okay, you can put it up here. And then here you split it. Okay, I think maybe here you don't split because here you use bar. Otherwise, it should be four. Here maybe you can just whatever scheduling that you want to use. Okay? And they ask you to try different scheduling. We try. You may evaluate the performance using different schedulings. See which one is faster. Okay? I think this one is quite straightforward. You just need to put whatever that is given there, the source code. Everything is given to you. This one should be working code. What you need to put is just this one single sentence here. That's all. Yeah, and then you try different scheduling. See if you get any performance difference between the different scheduling algorithms. Okay? Okay, we finish here. We save first before we do. You can read now.